Hi, I am Núria Armengol Urpí, and I'm going to present the work on risk-averse offline reinforcement learning that we did myself, Sebastian Curi, and Andreas Krause from ETH Zurich. The main motivation of our work is trying to leverage the power of reinforcement learning agents into real-world applications. The main problem, though, is that the deployment of highly performing RL agents in high-stakes applications is limited by prohibitive large costs that occur at early exploration stages during training. To address this issue, the offline RL setting considers learning a policy from a limited amount of pre-collected data. However, existing offline RL algorithms are risk neutral, so they may sacrifice large but rare losses for the sake of performing well in average. For high-stakes applications, rather than focusing on the average performance, we would like to do risk-averse decision-making and give more weight to adverse events rather than to positive ones. Although several algorithms for risk-averse RL exist, none of them addresses the offline setting, but most of them are on policy, and hence we have again the problem of catastrophic events happening at early exploration stages during training. To address this issue, we present ORAAC, Offline Risk-Averse Actor Critic Algorithm, which is the first approach towards learning a risk-averse RL policy using only offline data. The algorithm has three components. The first component is the critic in red, which is in charge of learning the full value distribution Z. The second component is the actor in green, which is a risk-averse component and is in charge of creating actions that maximize a risk-averse distortion of the value distribution estimated by the critic. The third component is the variational autoencoder, VAE, in blue, which is an imitation learner that learns a generative model of the behavior policy to reduce the bootstrapping error arising due to the offline nature of the algorithm. Hence, the actions generated by the VAE, with high similarity to the ones in the dataset, are afterwards perturbed by the risk-averse component in the direction of maximizing the desired risk-averse criteria. We proceed to explain a little bit more the three components of our algorithm. Again, the distributional critic is in charge of learning the full value distribution, which we represent implicitly through its quantile function. We use this representation because many risk distortion operators can be efficiently computed using it. We parameterize the quantile function through a neural network with learnable parameters W, which given a quantile level tau and a state S and an action A, outputs the quantile value of the return distribution at the desired quantile level. The second block is the risk-averse actor. We consider parameterized deterministic policies optimized to generate actions that maximize a risk distortion D of the estimated value distribution. We can approximate the desired risk distortion D of Z via sampling from an associated quantile distribution PD. At this point, we already have a theoretically sufficient algorithm to learn a risk-averse policy, but when moving to the offline setting, the bootstrapping error appears. To this end, we decompose the actor policy in two components, an imitation learning component and a perturbation model. The imitation learning in blue is the third component of our algorithm and is implemented via a conditional variational autoencoder that learns a generative model of the behavior policy to reduce the bootstrapping error. Whereas the perturbation model generates actions to maximize a risk-averse criterion, and it is optimized using the actor loss that we reported earlier. Finally, the lambda is an hyperparameter that scales the perturbation magnitude. We evaluated the performance of our algorithm on the D4RL datasets. We used three Moyoko tasks, Halfshita, Walker, and Hopper, and we chose the medium and expert variants of these datasets. Since the tasks are deterministic, we incorporated the stochasticity into the regional reward function to have a meaningful assessment of risk. For example, in the case of the cheetah, we model the risk of robot braking due to speeding too much, and hence we add the penalization with some probability 0.1 in the case of the cheetah exceeds the speed limit V hat. Similarly, we do the same with the Hopper and the Walker if the pitch angle of the agents exceeds a threshold angle theta hat. In this experiment, we intend to demonstrate the effectiveness of our algorithm as a risk-averse learner in the offline setting. We compare ORAAC optimizing the risk distortion CBAR at quantile level 0.1 to different benchmarks, namely ORAAC optimizing other risk distortions, a competing risk-averse algorithm, a state-of-the-art risk-neutral agents, different ablations, and the behavior policy. We see that for all three tasks, Halfshita, Walker, and Hopper, and for both variants, medium, and expert, ORAAC 0.1 has higher CBAR than benchmarks. and also that when optimizing for other risk-averse criteria, still has good 0.1 CBER performance. We also show a qualitative evaluation of the risk-averse performance by looking at the support of the risk events. We see the frequency of different velocities for the half-sheet and different angles for Hopper and Walker, and we show in green the risk-free region. In purple, we show the behavior policy, and we see that most of its support lies out of the green area. When looking at the distribution induced by ORAAC, we can see that it learns to shift the distribution towards the safe area, whereas OD4PG, which is risk neutral, ignores the rare penalties and imitates the behavior distribution, having most of the support in the risky area. We visually show performance on the half-sheet task for the medium variant using our algorithm ORAAC and a risk neutral algorithm OD4PG. While the risk-neutral algorithm ignores the high but rare penalizations due to speeding too much and runs as fast as it can, ORAAC keeps braking and never exceeds the speed limit. To sum it up, we just showed the first fully offline algorithm for risk-averse reinforcement learning that is compatible with many risk-averse criteria, outperforms algorithms in terms of risk-averse performance, and is competitive with risk-neutral algorithms in terms of risk-neutral performance. Thanks for showing interest in our work, and please read our paper or drop us a mail for further information or comments.